organized by Research Center for Physics, Indonesian's Institute of Sciences. So this is our 9th colloquium, and we regularly hold the colloquium at least twice a month, inviting both from internal and external researchers with various background of expertise, from material to high energy physics. We are very honored to have with us today Professor Katsushi Hashimoto from Department of Physics, Tohoku University. Thank you for coming and accepting our request. Today he is going to give a talk about scanning probe microscopy of macroscopic quantum phenomena, microscopic roles of wave function, and electron nuclear spin polarizations on quantum Hall effect. Please feel free to ask questions at the end of the presentation directly, but do not forget to turn the audio on beforehand, or you can simply drop your questions at the chat box, and I will happily read the question for you. So before we start off the talk, let me briefly read our guest speaker CV. Dr. Katsushi Hashimoto is an assistant professor in the physics department at Tohoku University. And prior to joining the faculty, he was a researcher at NTT Basic Research Laboratories, working mainly on electron nuclear spin interactions in quantum Hall effect. And then he went for a postdoctoral research in Roland Wiesendager Group at Hamburg University of Technology, where he developed ultra-high vacuum scanning tunneling microscopy at low temperature and successfully imaged a very clear quantum Hall transition in real space for the first time. So yes, so let's start the talk, please.
Okay, thank you very much for introduction. So first of all, I would like to thank the organizer, especially Fauji, to invite me this colloquium of RIPI. So today I'm going to talk about the scanning probe microscopy of macroscopic quantum phenomena. So basically, wait a moment, this is a 1 hour, right?
Yes,
I have to check the time, because otherwise I hope I should finish. I can finish the on time. Okay. Actually quantum phenomena here it's a quantum Hall effect, which is emerging high magnetic field at the low dimensional system, especially two-dimensional system, electron system. So, this effect is really depends on microscopic, especially, let's say, quantum Hall, like a wave function, and also even, electron spin polarization, and also nuclear spin polarization as well. So, okay, so let me start the introduce the quantum Hall effect. So I think that some of you know the quantum Hall effect probably. It's found by the Professor von Klitzing, who. Oh. So, is it okay? Okay, so he got a Nobel Prize 1985. So here you can see the what is the quantum Hall effect like. So basically, as I already introduced, quantum Hall effect arises under the when electron two-dimensional electron system experience the strong magnetic field, perpendicular strong magnetic field. So normally to measure the quantum Hall effect, we use the so-called whole bar structure, whole bar sample, which laterally confine the to the electron system here like this. And we can flow the current from the source and from source to the drain. And then simultaneously, we can measure the longitudinal voltage as a function. So then longitudinal voltage strongly oscillate as a function of a magnetic field like this. And also we can measure the transverse resistance, so-called Hall resistance. It shows the quantized step like this. So this is a transport measurement, the transport data of quantum Hall effect. So under the high magnetic field, electron make a so-called cyclotron motion within a 2D system. And especially at the high magnetic field, the radius of this cyclotron motion is very, very become tiny. And also, let's say quantized, which described by the here. So Planck constant and also magnetic, which determines the Planck constant and the magnetic field, and also integer value. So for instance, at high magnetic field 12 Tesla, this the cyclotron motion rate, the radius become only nanometer scale, 7 nanometer, very small. So this means electron is it's like confined the really small space, nanoscale. So consequently, the continuous 2D electron density split into the so-called lambda level, like this. Can you see? And further, okay. And also, we can calculate the wave function of all of the level. For instance, at the lowest lambda level, the wave function in a real space looks like this, just like a mountain. And first, next lambda level, we call the LL1. It looks like now looks like a dip structure, and finally, rather higher round level, you can see the a ring and also mountain structure, dot structure. So, but size, length scale is again, it's like 7 nanometer at 12 Tesla. So, so you can imagine that actually this is a similar similar to the wave function of a confined a function which is confined atoms. You run the probably in the textbook. For instance, one S state orbital shows the just a spherical, and but a P, D, F. This shows the a very complicated a wave function. So its tendency is similar. Okay. Anyway, okay, maybe. Oh, didn't. Okay, so I cannot show here, but it's actually further split into the shows the spin splitting at the really high magnetic field. Each random level split into the spin up and down as well. Okay, so this special, let's say special wave function has a very much more interesting a physics, another physics. So it's like a topological a characteristics.
Astaga, Astaga.
Sorry, any question? Is it okay?
Yeah, sorry, there's some disruptions. Please continue.
Okay. So actually, the quantum Hall wave function has let's say topological characteristics. For instance, here you can see the let's say you can imagine this is a quantum Hall system which is confined within a sample or Hall bar, which I introduced previously. So actually, at the quantum Hall state, bulk region, bulk of a sample, center of a sample, it's become insulating, like outside. Of course, outside is a vacuum, so it's insulating area region. On the other hand, edge of a sample, the so-called edge mode or edge channel appear, which is metallic states, and a current can flow only edge in this case. So actually, this quantum Hall state, metallic phase at the edge and the insulating phase at the in the bulk region, it's topologically protected. So you can imagine that the top inside insulating phase, quantum Hall phase has a special topological state, so that can be like you know, a Möbius loop, and topologically, you know, it's a special shape, right? And on the other hand, outside is let's say normal insulating phase. So it could be just a simple loop. So when you change the this Möbius loop to the normal loop, you need to cut and rearrange. Actually, this state corresponds to the, it's not insulating phase anymore. It's a metallic phase. So this is a very simple explanation of a topological state of a quantum Hall state. Indeed, it's difficult to imagine what is a topological feature in quantum Hall, but okay, I found in some journal. So actually, quantum Hall wave function has a let's say twisted, like this kind of twisted pattern. Actually, not in real space, but in momentum space. So this corresponds to the like Möbius loop. Okay, anyway, actually, this topological physics matter is not only for quantum Hall, but quantum Hall is a really old, let's say old or fast found topological matter. But recently, other many topological system has been found, like a quantum spin Hall system and the quantum normal Hall system. Yeah, so topological insulator, you know, many things. So, but anyway, this is also very interesting physics in quantum Hall. So actually, such a metallic edge state appear in a quantum Hall state. So this is like a cartoon. What is a electronic feature inside of a Hall bar? So when a Hall resistance shows the plateau, this means a quantum Hall state effect. So for instance, at the we call when this system become a quantum Hall state, we call you know, this is a filling factor 1 or 2 or 3. So integer filling, close to the integer filling, actually we have a edge metallic state which is drawn by the gray region. This is a metallic state here. And the inside, there is most of them show the white. That means the insulating phase. So actually, that's what I explained in a previous slide. So in this situation, we see a quantum Hall effect. Okay. Okay. So anyway, our purpose is that this is just theoretical, either theoretical or just expecting cartoon. So we want to really see the this insulating phase, and also even nanoscale wave function of a quantum Hall. So in order to the end, I use the several system. So today I will show the results which obtain Hamburg University using a high magnetic field, low temperature UHB STM system here. And here, using this system, I observe the wave function. We perform the wave function mapping, and also which shows the quantum Hall transition. And also, we recently built the high magnetic field, low temperature scanning gate microscope, and even scanning nuclear resonance microscope. This is a very unique microscope in Tohoku University. So using this system, we visualize the H channel or quantum Hall H channel, and also influence of nuclear spin polarization and also electronic spin polarization on quantum Hall effect. Okay, so I will first start this wave function mapping. So I use the several microscope, but first, this is just a basic, very most fundamental basic scanning probe system, scanning a tunnel microscope. So maybe I think most of you don't know scanning probe so much. So let me explain briefly. So scanning tunneling microscope was invented by the Laura and Professor Laura and Bining, who got a Nobel Prize in 1986. So structure setup is very simple. Just you need a sharp tip. Okay, just doesn't matter. You can even cut wire, a narrow wire by the some prior, and then you get this kind of sharp apex of metallic tip. And if you approach the metallic tip onto the sample very close, like let's say less than 1 nano or even few angstrom range scale, then you can tunneling current flow from the tip to the sample. So because tunneling current is very sensitive to the distance between the tip and sample, so eventually you can you can scan the tip can scan onto the atomic corrugation of surface. So that's why you can see this kind of a very beautiful atomic structure. But actually, the advantage of a scanning tunnel microscope is not only imaging atomic structure, but also mapping. You can map the local density of state of electronic system. So, for instance, if you take differential conductivity (dV), which is actually proportional to the local density of states of a sample, and then as you imagine, we can map the electronic wave squared electronic wave function So, because we can scan X and Y direction, so by the, here I say nanometer, but I mean, using a scanning tunnel microscope, normally sub-angstrom accuracy, we can, scan. And we can, anyway, make a wave function mapping. And also, we can sweep the sample voltage, which correspond to the sample the energy of a sample a electronic state. So we can make a spectroscopy as well. So finally, we can map the wave function at a different energy. So this is the advantage of a scanning tunnel microscope. Okay, this is let's say monster equipment of Hamburg, which built in Hamburg University. So as you can see, even ceiling, we have a hole. So because we need, when we remove the insertion, which normally located within a cryostat, so like this. So which includes the cryostat and also STM. So then we need to go to the second floor and pull up, lift up by crane. Anyway, using this monsters equipment system, we can cool down sample to the 300 millikelvin, and we can apply magnitude 12 Tesla. And also we can prepare the very clear environment, or like 10 to the minus 10 millibar, ultra high vacuum. Okay, this is a sample to study to make a let's say surface two-dimensional electron system. So we deposit the cesium alkali metal onto the one of the semiconductor, indium antimonide, and then cesium become like a dopant. So two-dimensional electron system is confined within the surface. And then we can we are allowed to plot the two-dimensional electron, the local density of state of a two-dimensional electron system. So as I already introduced, applying a high magnetic field, continuous density of state to the two-dimensional electron system, continuous density of state, split into the lambda level, and also split into the further split into the spin up and down. So first to check this, we position tip onto just a single point, and then made a single point spectroscopy. So as you can see, first we see a continuous local density of states like this, and then it's split into the a pronounced peak, which correspond to the cyclotron each random level, and also a small splitting, which correspond to the spin up and down. So finally, it's really grow to the very beautiful a spin splitting random level. So I did, it takes time to measure this kind of thing, but each magnetic field, I did a spectroscopy with a very fine magnetic field step. And here I plot the, made a color scale plot of DIDB, local density of states, as a function of magnetic field and also energy. So you can clearly see the so-called Randall Fan diagram, which you can see in a textbook. Okay, so next, okay, what in especially real space, how can we see the quantum Hall states? So we really want to approach the wave function of a quantum hole. So actually, in a sample, the sample is not flat for two-dimensional electron system because within a semiconductor system, there is a potential, so-called potential disorder, which could create a potential hill or potential valley for electron system. So important thing in the quantum Hall effect is that how electron move around the such a quantum potential disorder. So this is like a classical motion. Left figure shows the panel shows the classical motion of electron around the potential maxima. So first, electron move. Electron performs the cyclotron motion, as I already explained. But because electron feel the electric field, because of a potential hill or valley perpendicular to the this motion, cyclotron motion, then the electron drift to around the potential maximum. So this is finally it make electron path within in a quantum Hall state. So then this is classical picture. So if we can replace this cyclotron motion as a wave function, which I introduced already. So for instance, if the situation is LL0, lowest random level, then this like a mountain-like feature structure drift along the potential maximum means just we can drag the this mountain. Then you can imagine that we get a this creates a line, just a single line structure around the potential maximum. On the other hand, what about the higher random level, LL1, so which have a wave function, a deep structure of a, or let's say ring structure of a LL1 wave function. And again, let's drag the this ring-like structure to the one direction. Then we get this kind of a double line structure around the potential hill. And LL2, we have a more complicated structure. So then, as a result, we get simply three straightforward line structure around the potential maximum. Okay, so first, let me show the simulation. A result of a simulation of such a feature. So as I said, quantum Hall, a semiconductor has a potential disorder. So here in a simulation, we assume the this kind of potential hill and potential valley. Then we calculate the quantum Hall state, and then you can see the like a ring-like structure, which encircled by the potential disorder. So this is a simulation calculated drift states. LL0, as I already showed, you can see the like single line meandering around the potential. And then LL1, okay, it's really difficult to see, but if you really take a look, there is a 2 line here, and then LL2, 3 line here. So this is a cross-sectional. So which clearly shows the single, double, and the triple line structure. So okay, this is a, measurement result. Measurement result is much more complicated because potential disorder is much more complicated. So then LL0, it's clear. You can see the single line, which really encircle around the potential. And the LL1, okay, now it's start smelling. But anyway, can you see it's really complicated structure up here and the LL3. So it's really hard to see, but you can imagine it's really fully, complicated wave function. So actually, this is my result. Actually, using Fourier FFT, we can in this paper I really demonstrate that this is a indication of a wave function of quantum Hall. But actually, afterwards, my former colleague of Marcus Morgenstern group in Aachen University, he succeeded making a very nice, clear real space wave function structure of a quantum Hall wave function. So you see here, you see a line, just a single line structure and circle potential. And this is here is you can see double and also even triple. So and then in this case, he also used the similar system, Sejm on indium antimonide, but recently even other system for other topical a system like a 2D system in Bismuth. Even this system, the more clear, very beautiful ring-like structure observed. This is a kind feature of like a wave function of a quantum Hall. Okay. Okay. So using this ability, we wanna next we wanna approach the so-called quantum Hall transition. So again here, okay, this time I show the magnet conductivity, which measured by the Corbin disk, so-called Corbin disk, not the Hall bar, but a Corbin disk. But anyway, here what you can see is that as a function of a magnetic field, again conductivity oscillate. So here you can see the conductivity completely vanish, and also next higher magnetic field it's recover and then vanish, recover, right? So conductivity zero means system become insulating, and also conductivity finite means a metric. So this is actually like a quantum Hall transition. Insulating phase make a transition into the next insulating through the metric phase. So okay, we don't have so much time. I will simply explain what is the quantum Hall transition. So actually, quantum Hall transition is one of the so-called two-dimensional quantum phase transition. So which includes not only quantum Hall but also disorder-driven metal-insulator transition, and also even superconductor insulator transition. So they, when these system make a transition from first insulating phase to next, this insulating phase is characterized by the so-called localization length, where electron is really localized. So when it's make a transition through in between, the system become, this localization length exponentially increase. That means it creates symmetric states. So this is a so-called let's say quantum phase transition. Okay, so let me show the experimental result, how a quantum Hall transition occur within a nanometer, 60 nanometer scale. Okay, this range is like 120 nanometer scale. No, more, 150, let's say. Okay, so what I did here is that I measure the local density of state. I map a local density of state at each energy, which across the random level. Okay, let me show. Oh, I can't do it. Wait a moment. Here. Okay. First, here you can see the dot-like structure, and then it become a ring, and then it expand, and connect each other, and then again shrink. Okay. So once more. So this dot structure means here we have a electron density, local of density of states. That means black area we don't have an electron. Bright area we have an electron. And the first electron shows the electron system shows the ring, and then it expand, connect each other. This is a nanoscale feature of a local density of state in a quantum Hall. So what we see is that at the lowest lower side tail of a lambda level, the bright ring structure appear. Actually, this is indicates here electron drift along the potential valley, and higher energy side of a tail of a lambda level, we see a different ring-like structure. So this indicates the drift motion along the potential here. And finally, in the center of a lambda level, we see a network-like structure. So as you can imagine, here because the electron cannot jump from this guy to this guy, so that means the phase system become insulating, and the right side panel also show similar. But on the other hand, network structure, of course, electron can pass through the all of the area, so this could be a metric. So this is this is actually a microscopic structure of a quantum Hall transition. So actually, what I show such a thing first time, but afterwards, a similar way is applied to the other, very interesting sample. So in this case, graphene, even graphene, this is also 2D, right? 2-dimensional system shows the quantum Hall state, which even shows the drift state. And also topological insulator, bismuth selenide. That also shows a very beautiful evolution of a ring structure. This is really like a wave function of quantum Hall. Okay, so next let me move on to the quantum Hall H channel, visualizing a quantum Hall H channel. So what about? Oh, okay. I should hurry up. Okay. So as I introduced, the in the quantum Hall regime, H channel is very special. Like it's topologically protected. So very interesting states. So left side, I show the, let's say, classical picture of H channel. So again, this is like a Rundle level as a function of space across the x direction, and which shows the Rundle level feature energy diagram. So so because we have a confinement potential on the in the edge of a sample, so Rundle level is really, you know, a move up in the both sides of edge. And when the Fermi energy locate in between Rundle level in a bulk region here, for instance, somewhere here, of course, bulk region it's insulating, but edge within the edge, Fermi energy across the Rundle level. So that's why electron current flow, the edge become metallic and the current flow the only edge in this case. But this is actually classical picture. So real picture is much more complicated, unfortunately. So here you can see the schematic of again Rundle level, real picture of a Rundle level on the edge region. So for instance, if again we have a Rundle level, several Rundle level, and a within a potential confinement over edge. So here there is a Fermi energy. So when the wait a moment, when the Fermi energy close the Rundle level, so here is should be a metallic. So this metallic part, because the electron can move, so it's completely screened, electrostatically screen the electrostatic potential of a confinement of a sample. Then the Rundle level become flat. On the other hand, here the region where a Rundle level fully occupied means the Fermi energy is within a gap. So then this region become insulating, and then potential cannot be screened, and then again this become show the Rundle level tilt. So that means on the edge you see a step-like structure, and each metallic phase and the the insulating phase is so-called a compressible region and also incompressible region. This is a stripe structure of a compressible and incompressible region, metallic and insulating strip region is a real picture of edge channel. So we again move back to the this figure. So anyway, here we can see the some, let's say, complicated structure edge channel. So for instance, again, this gray region, it's a metallic. It's a little bit above the integer filling factor. The edge again is a metallic, like a gray region. But next to edge, you see a insulating region. This is what I explained as a incompressible region, and then again metallic. So, but if the quantum hole, the filling factor close to the integer filling, as I already introduced in the beginning, metallic state, we have a metallic channel outside, but it's incompressible region, insulating region spread into the bulk. Although there is a compressible metallic puddle, but anyway, bulk is insulating and edge is metallic. So actually, this transition is just expected one. So, but okay. Now we have a probe system, so we wanna access the system. Okay, so this in this system, in the beginning, I show the I use the STM, but in this system, because we need a high mobility gallium arsenide quantum Mao, which is really a locate, not surface, but 100 or 2000 nanometer below the surface. It's actually capped by the top layer to keep the high mobility. So in this case, I cannot use the STM because the tunneling current cannot pass through the top insulating layer. So instead of that, we use the so-called atomic force microscope. And here, what are our ways that we, again, here we use a metallic tip, but we use this metallic tip as a, let's say, local top gate. So that means if we apply the DC bias here, so then we can stimulate electrically, we can apply the small amount of electric field to the local region of a two-dimensional electron system. And then probably quantum Hall state can be disturbed. And then we measure such a local disturbance using resistive detection, means just a transport measurement. And with scanning tip, we can map the, let's say, some electronic, H channel. So here we use the, again, as I said, atomic force microscope combined with the dilation refrigerator. And here you can see the heart of atomic force microscope, which is made by the so-called tuning fork. And the point, this is actually tip, which using this tip, we access to the sample. So we can cool down the 100 millikelvin down to 100 millikelvin and up to apply magnetic field up to 8 Tesla. Okay, so here what we observed. So we actually what we disturbed is that scattering. Maybe I should not fully explain, but because time is limited. So, but simply we induce here some scattering within a incompressible region where we expect there is a insulating strip. So what we can visualize is that this is an incompressible insulating strip. So at the filling factor 2, you can see the very clear H channel. Okay, so now we see check the such a H channel or incompressible region strip, which actually evolve as a function of a filling factor. So as I already explained, the slightly above the filling factor 1 integer filling, the incompressible region shows the strip line. So, but it's spread into the bulk and make a puddle-like structure. So this is what we really observe here. So above filling factor 1, we see very clear line structure. Then it's spread into the bulk region and finally show the bulk and puddle structure. Okay, so this kind of observation, H channel observation is applied. Okay, here the method is a bit different, but nowadays we can see even H channel on graphene and also quantum spin hole system in a traditional metal dichalcogenide. you can see clear H channel. Okay, we don't have a time. So okay, this is a last topics. So actually, nuclear spin. Nuclear spin normally isolated from the electronic state, so quantum Hall state. So normally you can't see such effect. But at a certain a condition in a quantum Hall state, you can see the resistance enhancement or large hysteresis by a nuclear spin polarization within a two-dimensional tone system. So actually, that is already confirmed by the so-called resistively detected NMR using a transport measurement, and we can apply the RF magnetic field from the coil. So you can see the this resonance, nuclear spin resonance. In this case, nuclear is a host material of quantum well, gallium arsenide quantum well. So that's why you see arsenic and gallium nuclear spin resonance, which is measured by resistance. So in this case, hyperfine interaction is important between the electron and the nuclear. And this first static, dynamic term indicates the when electron spin is a flip, nuclear spin is flop. So thereby, nuclear spin polarized, dynamically polarized. And so using this term, we can actually just flow the current, and by flowing a current, we can polarize the nuclear spin. And on the other hand, first term, static term indicates the so-called Oberhauser field. So it's change the electrical resistance. So that means we can polarize the nuclear spin using current, and it polarize the nuclear spin, change the electronic system, and then we can measure the nuclear spin polarization by just measuring resistance. So this is an example of such a dynamic nuclear spin polarization and also detection. So when the in a quantum Hall state, we can flow the relatively large current, then H, okay, maybe I should skip H near the H, because of flip-flop process, nuclear spin is polarized only along the H.
Shimoto-san, we can extend the talk. Don't worry.
Yeah, but okay, a little bit hurry up, but already past 1 hour. Okay, 10 minutes.
We can extend. We can extend after 10 minutes.
Yeah. Okay. Okay. Anyway, so question. Okay, so we can expect that nuclear spin polarization in this case nearby the edge of a Hall. So here natural it's natural that I just wanna observe this kind of dynamic nuclear spin polarization, how it's distributed. So probably you imagine why we have there are maybe NB center scanning microscope. This might be measure the nuclear spin magnetization of a nuclear spin. And also actually there is several way to measure the nuclear spin polarization using, in this case, using STM, very elaborate work. But all of these method can be applied only for detecting very surface. They are very surface sensitive measurement. So these measurement can only detect the a nuclear spin which locate on the surface. On the other hand, I already introduced our sample. Within our sample, we expect that the nuclear spin is polarized within a two-dimensional electron system channel, which locate 200 nanometer below the surface. So we cannot access, it's not surface anymore. So we need a different measurement, different way. So fortunately, we have a technique like resistivity detection, which means, as I already explained, when the electron pass through the nuclear, if nuclear spin is polarized, electron feel the nuclear spin polarization through the hyperfine interaction, and then electron system modify, and we can measure by measuring a resistance. Okay, so again, we can use similar system based on atomic force microscope. And we apply, this time we apply the not static electric field, but RF electric field onto the tip. So here we wanna use the resistivity detection of nuclear spin polarization, which I already introduced. But then that is not a local measurement. So for local measurement, we wanna induce the nuclear spin resonance only below the tip. So that's why we apply the locally apply the RF electric field. So then this is our condition. We focus on so-called breakdown regime of filling factor, means relatively large flow the large current. Thereby, there we can polarize nuclear spin polarization. So again, as I already introduced, in this situation, we can polarize the nuclear spin only along the edge. So okay, let's observe the this nuclear spin resonance. First, here what I did is that the position tip on the edge, and then sweep the RF frequency electric field. Then we observe the very clear the resonance, arsenic nuclear resonance. On the other hand, position 2 and 3, we cannot see anything. So this is a color map of amplitude of resonance. So as you can see, clearly you can see the dynamic polarization, nuclear polarization occur only along the edge. Okay. So actually, I don't explain so much, but because of quantum Hall, this is a quantum Hall physics, but this is a nuclear spin, the region of a nuclear spin polarization change from the edge to the bulk region. So we can even polarize nuclear spin all of the bulk region. So okay, this is the final, really final topics. So we can even observe the electronic spin polarization using this nuclear spin, which is polarized within a bulk. So here again, this is the amplitude image of a nuclear spin polarization. So what I did here is that we measure the resonance signal at each point. So for instance, a right side you can see the each signal resonance spectrum observed at across the several points marked by the red cross. So starting from the upper region, okay, first you can see the relatively large resonance at close to the 115.73. But as going down to the bottom, the resonance frequency goes down. Actually, this shift is so-called night shift of nuclear spin resonance. So this night shift value is actually proportional to the electron spin polarization. So we can determine the electron spin polarization at each position. So here, for instance, upper region, electron spin polarization is 80%, but it goes down to the 60%. So the color scale map of night shift is shown here. Actually, this right side to a figure panel shows the corresponding color scale plot. So at the upper region, we have a relatively high electron spin polarization, but it quickly goes down within 200 micrometer. And close to the so that means that here we see a really strong variation of electron spin polarization. But at the close to the quantum Hall regime, means lower current region, we see the most of region shows the really high electron spin polarization, because this state is the so-called filling factor 1. We expect that all of the electron spins are polarized. So that's why we see a high electron spin polarization. Okay, so this last part is actually, our what are we expect is that we wanna really develop microscopic so-called MRI within a device, very small scale. So indeed, now today's organizer Fauji already found that such a nuclear spin polarization occur close nearby the so-called quantum point contact device. So now I apply the same way, and I see some this is just so not a real measurement, but like a test measurement, but a preliminary result, and I see some like a night shift spectrum. And also I wanna apply this system in, and even manipulate, because we can apply the electric field, RF electric field. We wanna manipulate the single nuclear spin within a semiconductor and also molecular system. Okay, so let me summarize. So today my message is that to really understand the macroscopic world, which we can really see in, for instance, in the transport measurement, we really study, investigate, examine the microscopic world, which includes the electron which confined in small region, which shows the wave function and spin variation, and even correlated with the nuclear spin by using a scanning probe. So in that case, scanning probe technique is a very powerful tool. Okay, thank you very much for your attention.
Thank you very much, Hashimoto-san, for a
1
very
hour.
nice talk on the, no problem,
Pretty 1 hour.
visualizing the wave functions and other stuff using scanning probe technique. Now, questions is open, so feel free to ask the questions if you have. So, okay, so we have 1 or 2 questions from from Ahmad Nugraha.
Okay.
The first question is, sorry if I missed this part. The quantum Hall transition from the localized to extended states can be spatially resolved by scanning tunneling spectroscopy down to the quantum Hall wave functions. And the
Yeah,
question is that what about the time dependence of the wave function?
time dependent. Time dependent. Ah, okay. Time dependent is very, but what time dependent means? Time dependent means um yeah, actually I don't know exactly what is time dependent, but basically, you know, how can I say but for instance, here if we fix the uh, なんだろうな、energy, in this case, energy and the magnetic field, then basically this quantum Hall state is like a static, not a, doesn't change as a function of time. Yeah, maybe I misunderstood, but anyway, okay. Anyway, if even though there is a time variation, maybe it's really tough to probe using a STM, conventional STM, because normally, you know, for instance, in my measurement, this this mapping, you know, it takes like a couple of hours to get this kind of, you know, means that it takes time to get a thing. But recently, we have actually, I'm collaborate with the other STM guy. We recently developed the ESL STM. So in that case, we can apply the gigahertz frequency electric field or RF field. Then we can access the, it's not time dependent, but yeah, maybe we can say, you know, because we can observe the some electron spin precession. So in that sense, maybe time, not perfectly.
Right.
Okay.
So to resolve this time dependence of the wave functions, anyway, you need a faster measurements.
Exactly.
Because the dynamics might be really, really fast.
Yeah.
I see. Okay, thank you. And another question from the same person is that, okay, so in Indonesia, funding agency often asks for a short-term or near-future applications of such fundamental research like what Hashimoto Sensei is doing.
Okay.
And the question is that, do you have suggestions what kind of near-future applications we can have by utilizing quantum Hall systems?
Using a quantum Hall system?
Yeah, so what kind of like future applications?
Yeah, basic research. No? Yeah,
right.
I think you know, yeah, first thing is that this kind of what I introduced today is not only a quantum Hall, but also, you know, okay, in the case of graphene, this is, let's say, quantum Hall, but also graphene has a different, you know, type of Dirac fermion. But anyway, you know, different, more, we can apply the more interesting, not only semiconductor system, conventional semiconductor system, but also, you know, this exotic, let's say exotic, newly arising material, emerging material like a graphene, and also topological thing. This is one direction. And also another direction is that even, you know, in a quantum Hall states, did I? Maybe, you know, still there is a interesting feature, you know, let's say again, this is also topological, but topological spin structure so-called skyrmion, which actually recently this skyrmion is observed in a metric system, but even quantum Hall, we have this kind of a very interesting topological states. So, it might be possible that we can observe this kind of exotic, exciting physics. Okay.
I see.
Yeah.
Thank you very much. So any questions from the floor? So I have one question on the first part of your talk.
Okay.
About the quantum Hall transitions. Can you extract the prefactor of this so-called the
alpha?
Alpha.
Exponential.
Exponential power factor. Yes, exactly.
Yeah, that's actually what we wanna do it. And maybe if we could get this kind of thing, maybe science, but it's not. It was not.
Yes, so there's some sort of like different sort of predictions, right, about this number itself from 1.7 up to 2 point something.
Exactly. Yes. So what I remember is that if point is that if this is a classical system, classical, it's based on based on classical mechanical system, then this exponent is lower, like if I remember correctly, like 1 point something.
Right.
But in a quantum Hall system, because this is a quantum system, so we expect 2.3. What is the special? Is it did we have? Wait a moment. If we have, I have. Maybe I don't have. So because do we? No. Okay, no figure, unfortunately. Okay, anyway, because point is that when it's make a transition from localized to extended states, first, this sort of a connection should be, if this is a quantum system, this should be a tunneling done by the tunneling process, process. So that is a key point to get a higher value of a critical exponent, like a 2.23. So although we didn't get analyze such a critical exponent, but we found that there's some sort of an indication of a tunneling between
I see.
Yeah.
Between
so in that sense,
networks.
Yeah.
I see.
Okay.
Thank you very much. Any other question from the audience? Okay, so there is one more question. Sorry for asking one more question. Can the nuclear resonance technique be also used for the materials with fractal Hall effect, like more 2D materials, twisted bilayer graphene, twisted graphene on hexagonal boron, and
you said first thing is that the fractional?
Yes, so the question is, can the nuclear resonance technique be also used for other materials? Like 2D system, like bilayer graphene, twisted other.
Good question. Good question. That's another direction. Yeah, actually for graphene, good question. Graphene, it's a bit tough because graphene 12, carbon 12 doesn't have a nuclear spin. But we can prepare the carbon 13, 100%, not 100, 99% carbon 13 graphene. So that's using that one, maybe we can observe. And another thing is that even topological thing, some of the material show the reports that for some of material the nuclear spin effect was reported. So in that case, we can maybe apply, but yeah. So but anyway, first we need to make a nuclear spin polarization. So in that sense,
Right.
yeah, challenging, but anyway, we
Right.
can. That is another direction anyway.
So yeah, so the most important part is that we need to have like a relatively big hyperfine interactions between
Exactly.
yeah, nuclear spin and electron spin.
Yes. Yes.
All right.
That's right.
Thank you.
Yeah. Hyperfine interaction. Yeah. Exactly.
So there is other questions from the audience. Just a simple curious questions. Is it possible to coherently control the nuclear spin in the structure?
That's what I want to do using this probe. Yeah, basically nuclear coherent manipulation of a nuclear spin is already done, right? I mean, even recently, I think NB Center is a much more nice system. You can even access the single nuclear. And also, but even semiconductor, I show you. Last one. This one. So actually, this one, this Nature paper shows the. In this case, they make just a single antimony nuclei into the semiconductor, and he apply. In this case, they apply locally. They use a local gate, local gate, but which fabricate on directly fabricate on the surface of a semiconductor. So they actually succeed found a coherent oscillation. In this case, they say they really manipulate single, but they didn't see.
It's hard to say.
Yeah, to see that, I wanna use the probe, and using probe, maybe I can visualize single spin,
Right.
and also we can manipulate. So that's actually future target.
Future directions. Thank you very much.
Yeah.
Is there any questions from the audience? One more questions, short questions, if any. So if not the case, I think it's time. Thank you very much, Hashimoto Sensei, for the nice presentations and accepting our request to to give a talk here.
Okay, thank you.
Okay, so please stay tuned again for another interesting seminar from different researchers, from internal or also external researchers. So let's thanks. See you again. Bye-bye.
Okay, thank you very much.
Thank you.
Thank you very much.
Thank you very much. Yeah.
Yes.
See you again.
See you. Bye-bye.
Thank you.